Our final topic of the semester, orthogonal bases. Set of vectors in an inner product space V is said to be orthogonal if every pair of vectors in the set is orthogonal. Each vector is orthogonal to every other vector in the set. If in addition to this, each vector is also unit, then it is called orthonormal. And if that set happens to be a basis, then you have an orthogonal basis or an orthonormal basis, respectively. Was a troll to want you to decide not to show today. It's like, ah, here's the exam solutions. Should get an easy A.
Did you give up any, like, the yellow sheet?
I did last time.
Do you have any extras?
I did pick it up after. The problem is I think the solutions to the exams are like, I remember it's like 8 pages. So I mean, that out of good memory.
I'll take my chances. I'll take my chances.
Or maybe I'll give you your own solutions to see if you're paying attention.
Is there any way you could post the actual exam 1 and exam 2 instead of just the solution?
No, because I plan on reusing the exams. I'm sorry. But also I want to let you keep the actual exam.
You're probably wondering what the hell what I was doing at 5 a.m. in the morning. I don't sleep.
If S is an orthogonal set of non-zero vectors in an inner product space V, then S is linearly independent. So if you have a set of vectors that are orthogonal, they're automatically linearly independent. As a direct corollary, V is an inner product space of dimension n, then any orthogonal set of n vectors would be a basis. So the idea is to form an orthogonal basis given an inner product space. And this process is known as the Gram-Schmidt process. Well, no. It was the QR factorization is done using Gram-Schmidt, but the first project was an alternative way of doing it. So no, you don't have to use it on the first project, but yes. If you actually looked up QR, it is the Gram-Schmidt. warn you, this process sucks. It is an awful process. However, still love it. Simply because of Schmidt. Best third baseman ever. Mike Schmidt. Schmitty. Good. It looks like you know what I'm talking about. My last section, no one knew who Mike Schmidt was, and I was very disappointed. I had to fail them all. Yeah, exactly. Best third baseman to ever exist. You know, it's objectively true. He's the best third baseman ever. Some say Chipper Jones, but that's BS. Chipper Jones is second. Schmidt's first. So we have a basis, V1 through Vn. Define a new set, V1, W2, W3 through Wn. W1 is V1, so I'm just putting V1 there. For Wi, Vi minus that sum for the i's between 1 and n. Then B prime defines an orthogonal basis for B. It's also not mentioned here, but these are ordered bases. Furthermore, if you define the set B double prime as V1 over the norm of V1, W1 over the norm of, W2 over the norm of W2, so on and so forth, that is an orthonormal basis. The Gram-Schmidt process itself is the iterative process of finding each W. That's the process. Depending on the inner product space, it's a massive pain. Since it is iteration, I can't see why you want to give a code the process to find each W. But even that might be a pain. Write the code for it. But we're not going to worry about that. We're just going to do it by hand. Subspace U of R4 is spanned by these three vectors: 1, 1, 1, 1, 1, 1, 2, 4, 1, 2, -4, -3. We want to find an orthogonal basis of U and an orthonormal basis of U. Well, we have a spanning set, right? Yeah, there's a typo. That was supposed to be B sub 1. I'm not going to. So we have a spanning set, right? For you. But is it a minimal spanning set? That we don't know. That we have to figure out. How do we do that?
Make each vector a column matrix and row reduce.
And how would it have to row reduce to be minimal?
It would row reduce to the identity matrix.
Well, this is impossible to row reduce to the identity. It'd be 4 by 3.
The only elements are leading ones.
So every column would be a pivot column. What happens if it's not?
Then one of the vectors is different with the common.
How do you decide which one? Or which ones?
The ones that don't have all leading ones.
Well, no rows are going to have all leading ones.
The ones that have an element to the right of the leading ones.
Columns that don't have the column, the non-pivot column is called that. Yeah, that's non-pivot columns. So what do you do with those vectors?
You have the free variable and parameterize the.
You're making the process too hard. Once you determine which vectors are a combination with the others, what do you do with them? You just get rid of them. Just throw them out. I think you were trying to
Find out.
find, I think you were attacking eigenspaces when you're trying to parameterize. Yeah, just get rid of those vectors. And what you're left with is now a minimal spanning set. Right? Good. Let's set up the matrix. Go reduce that matrix. What do you get?
Going by row, 1 1 0 0 1 0 0 0 1 0 0 0. I said the top one wrong. It's 1 0 0.
Should say. Is it a minimal spanning set? Yes. Which means that is our basis for you. Good, we have a basis. Now we can apply the Gram-Schmidt process. I'm going to start the slide actually. So the Gram-Schmidt process says you set W1 to be the first vector in your ordered basis. Now, which one you set to be the first vector is entirely up to you. But once you have an order for the basis, you're keeping that order throughout the entire process. I'm just going to stick with what they gave me, V1, V2, V3. Oh, that one was easy to find. Now the fun begins. W2 is V2 minus the inner product of V2 with W1 over the norm of W1 squared. Okay, so yeah, this was supposed to be, if I go back to the process, that was supposed to be a squared there, norm squared in the sum. Over the norm of W1 squared times W1. V2 minus, we're dealing with the standard inner product for R4, which is the dot product, right? Remember that? So we're taking the dot product of V1 and V2. Dot product is commutative. Actually, inner products in general are commutative, so it doesn't matter the order in which you do it. Because remember, W1 is V1. And who remembers how the dot product is defined?
Multiply the rows together and you add it all up.
Components multiplied and then the sum. 1 times 1 is 1, plus 1 times 1, you have 2. Plus 1 times 2 is 4, plus 1 times 4 is 8. Now we want the norm of W1 squared. Right, norm of V1 squared. Well, what's the norm of a vector? And do general, not with the standard inner product. How do you find the norm of a vector?
The square root of it, dot itself.
Again, ignore the dot product. More general.
The square root of its
Inner product of the vector with itself, which in our case is the dot product. But we want that squared. So aren't we just finding the inner product of V1 with itself?
Yeah.
What is it?
It's 4.
Then times V1. And I'll just write that is going to be 2. Theta, of course, 2, just so I don't have to waste space rewriting it. Now it's just the standard addition. 1 minus 2. 1 minus 2. 2 minus 2. 4 minus 2. There's your W2. A full derivative, I don't think it's derivation, I think it's a proof. Because the Gram-Schmidt process is just like when we did RREF. The process was developed in the proof. So the process is developed, so we're essentially proving the Gram-Schmidt process in the video. So just look through the video. It is again a pretty long proof, just like the RREF proof was. But it derives this process and why it works. All right, that was W2. We need W3 now. It's V3 minus the inner product of V3 with W1 over the norm of W1 squared times W1 minus the inner product of V3 with W2 over the norm W2 squared times W2. There's V3 minus V3 dotted with W1. Well, W1 is just all ones. 1 times 1 is 1, plus 1 times 2 is 3, plus negative 4 times 1 is negative 1, plus negative 3 times 1 is negative 4. Right now, over the norm of W1 squared. I already did that, so don't reinvent the wheel. Times W1 minus V3 dotted with W2. One times negative 1 is negative 1, plus 2 times negative 1 is negative 3, plus 0 is still negative 3, plus 2 times negative 3, so it's just negative 3. Negative 2. Negative 1 times 1 is negative 1. That's negative 3. 0. No, it should be positive 3. Why do I have plus 3 as? Oh, it's minus 6. Okay. Makes sense. Negative 3 minus 6, negative 9. Now we want the norm of W2 squared. That's just W2 dot W2. 1 plus 1, 2, plus 4 is 6. Times W2. So again, I'm just going to write in Brown.
Isn't the 6 squared? No.
If you take, so remember, it's the norm squared we're looking for, which is just the vector dot itself, because we're dealing with the standard. So you're probably thinking of finding the norm, which would be root 6,
Okay.
and then squaring that.
Okay.
And the fractions. Yeah, it's going to happen quite a bit in the Gram-Schmidt process. You're going to get hideous, hideous fractions. What is it? 1 plus 1, 2 minus 3 halves. 1/2. 2 plus 1 is 3. Minus 3 halves. It's 3 halves. Negative 4 plus 1, negative 3. And then we get what? Negative 3 plus 1 is negative 2. Negative 2 plus 3. There's W3. That is an orthogonal basis for you. Before proceeding, let me ask you this. What is the standard basis for R4? Lots of matrix. Is that orthogonal? Yes. Standard basis is orthogonal. That's nice. Oh, we're not done here though. Because they asked also for orthonormal. That means once we have our orthogonal basis, we have to normalize it. We already found the norm of W1.
The orthonormal basis is represented by B double prime
B double prime in the theorem.
in the theorem.
You can use anything that you want.
Okay.
Right, so another common one would be, that would represent orthogonal.
Okay.
And then if you want orthonormal, star, you may also see that. That's actually a notation that I used a lot. But I actually kind of like the time double prime better. But again, you can just use whatever you want.
All right.
We already found the norm of W1, right? Because we said the norm squared was 4. We also already found the norm of W2, right? Because we said the norm squared is 6. We just now need the norm of W3. One quarter and 9 quarters is 10 quarters. And then 9 and 1 is 10, so it's 10 quarters plus 10. 50 quarters. 25 halves. Yeah. The norm would be the square root of that. Five over root 2. Now remember, to normalize a vector, you take the vector, multiply it by 1 over its norm. We take the first vector, multiply it by a half. Take the second vector, multiply it by 1 over root 6. Right? Take the third vector, multiply it by root 2 over 5. And that would be an orthonormal basis. That is the Gram-Schmidt process. That was also in 3 vectors. Pretty sure you can imagine how tedious it becomes if your basis has 5 vectors in it, or 6 vectors in it. So let's look at a non-standard. We're considering the vector space P2 that has inner product, defined as inner product with G as the integral 0 1 f times G. Right? We work with that inner product later. I don't remember if it was on P2 though. I don't remember what the P was. But it was definitely that inner product. We want to find an orthogonal set with integer coefficients. That means we need a set so we can orthogonalize it. Is that even a term? Orthogonalize? It is now. Well, why don't we just pick the easiest set? What is the standard basis for P2? First you have to know the dimension of P2, so you know how many elements are going to be in there. Dimension is not 2. It's 3. Dimension is 3. Now what's the standard basis? Well, yeah, there's definitely 3 vectors in there, but what are they? No, they're not vectors in P2. I agree those are the coordinates of your vectors, but they're not the vectors themselves. Overthinking. Yes. Right. Again, those have the coordinates 1, 0, 0, 0, 1, 0, and 0, 0, 1. Maybe not respectively, depending on how you write your polynomial. That is the basis we're going to work with. We're going to use Gram-Schmidt on that. Start by taking W1 to be the first vector. 1. W2, V2 minus the inner product of V2 with W1 over the norm of W1 squared. All times W1. What is the integral of t from 0 to 1? That's the antiderivative. What's the integral? What? And half t squared, how do you evaluate that? Because you want the integral of this one. It's 1/2. Right? 1 squared minus 0 squared is 1 times a half. Ooh. Well, this one's really tough. What's the integral from 0 to 1 of 1? Ooh. That gives us t minus a half. Are those integer coefficients? Uh-oh, they are. 1/2 an integer. No. Uh-oh, that's not what we want then. Think in terms of, yes.
You just make it 2t minus 1.
Think in terms of geometry. You have two vectors that are orthogonal, means they're perpendicular, right? They intersect at a right angle. What happens if you multiply one of those vectors by a non-zero, let's just say a positive scalar? What happens to the vector when you multiply it by a positive scalar?
It just grows, but it keeps the same direction.
Define grow.
Okay. I don't know.
Because if it's the typical, if it's what you think of growing, if I multiply by a half, it's not growing. It's shrinking. So it only changes the length.
Changes the magnitude.
Right? Changes magnitude, but not direction, right? So then your vector would still be orthogonal. What happens if you multiply by a negative scalar? What happens?
It changes direction. Changes which way it's facing. Right?
How?
Turns
How does it turn? By how much?
180 degrees.
Just flips the direction, right? And would then change the magnitude. Right? -2 doubles it and then flips the direction. If I flip the direction of one of the vectors, are they still orthogonal? Yes, they are. Take the horizontal and flip it 180. Still orthogonal. The same is true for more generic vector spaces. That's why, yes, we just multiply by any scalar we want, other than 0. You multiply by any non-zero scalar and still have an orthogonal vector. Multiply your vector by 2. There's our W2, 2t minus 1. W3, V3 minus inner product of V3 with V1 over norm V1 squared, I should say W1, but same thing, times W1 minus inner product V3 with W2 over norm W2 squared. All times W2. Well, we already know norm of W1 squared. We calculated that already, that's one. What is the integral from 0 to 1 of t squared? 1/3. Write this in the ground. That's 2t cubed minus t squared, right? Integrate that from 0 to 1. For 2t cubed from 0 to 1, that's a half. Right? T squared from 0 to 1 is a third. What's half minus a third? 6. Now we need to integrate 2t minus 1 squared. Probably the easiest not to expand it and use u sub. U is 2t minus 1, that means du is 2 dt. Multiply your answer by a half. So let's first do 1/3 2t minus 1 cubed from 0 to 1. At 1, you get what? 1. What do you get at 0? -1? All right, -1 cubed. So 1 minus -1 is 2. That's not right. Oh, yeah. Times a third, so 2/3 is that answer? Now multiply that by half. You get 1/3. What is 1/6 over 1/3?
Two.
It's 1/2.
1/2, sorry. And you shouldn't need a calculator for that. Let's go this way. T squared minus a third. What is it? Minus t plus a half. What is a half minus a third? Are those integer coefficients? How are we going to make them integers? Multiply by 6. There you go. There's W3. Did you have multiply by 6? What else could you do with that? Any multiple of 6 would have worked, right? To clear out that denominator.
Is it 16? For the,
That should be 16. No. There's our orthogonal set with integer coefficients, which also happens to be an orthogonal basis, right, with integer coefficients, because we use the basis. Questions on Gram-Schmidt so far? I'm going to do this one. Because I realized I already proved that. That should be in the video. Finding coefficients, that's actually the Gram-Schmidt process. So, yeah. Here's what I want you to do. I'm going to pull instructor's prerogative. That is nasty. I don't want to do it. You have 20, just about 20 minutes left. Do that. And you can work together on it.